my name is Cameron Price-Jones and welcome to the video presentation component of. At the beginning of this assessment, it was determined that the basic model type of bridge that was designed to be constructed was that of a truss bridge that had the appropriate members that could withstand the tension and compression forces applied when tested. After reviewing various academic literatures, including other spaghetti bridge models and aligning designs with real-world truss bridge structures, it was decided that a bridge structure based off the Pettit truss design would be the design of choice. This is the Pettit truss bridge that the spaghetti model was based off. Using the Pettit truss as the basis of the model, one of the truss members was rearranged to span from the middle of the truss section to the top of the truss structure to account for the weakness and brittleness in the spaghetti and also the adhesiveness of the superglue. Also visible in this diagram are the estimated forces acting on each member of this bridge. The decision to utilise a truss bridge design was aided by the fact that the design includes braced diagonal members in each section, creating triangles and angles that add high amounts of strength when in tension to the bridge. In construction of the deck of the bridge, horizontal lengths of spaghetti, the picture shown here displays some of the rough ideas and sketches made early in the project, and it's visible to see that utilising the angled members of the truss design was key to the design of the model of the bridge. Before construction of the spaghetti model commenced, sketches of each individual section that would make up the bridge were made to a scale of 1 elevation sketches of the bridge model. Shown here is the plan sketch of the bridge model and also the sketch of the bridge deck, which are both drawn to a scale of 1:1. Once the plans had been drawn, it was time to construct the bridge using Coles brand spaghetti and Selle's quick fix superglue, shown below. Photocopies of the individual bridge component plans were created to use as a template to construct the bridge sections. Pens and pencils were also used to raise the spaghetti slightly off the template to prevent the spaghetti from sticking to the paper template. Once all the individual bridge sections had been constructed, it was time to begin the final assembly of the bridge. Firstly, one of the side pieces was laid down, again over pens and pencils to avoid the model from sticking to the table, and proceeded to lay one side of the bridge deck on top while gluing each aligning horizontal and vertical brace of the bridge and holding the sections in position as the glue set. Then repeated this with the other side of the bridge. Once the sides were stable, the 3 top bracing members were added and glued into position. As a last-minute decision, the 2 areas directly above the ends of the deck of the bridge were left open and unbraced to allow for easier installation and removal of the loading plate and eye bolt needed for the testing stage. The apparatus constructed to accommodate the eye bolt involves laying an 8 by 10 cm layer of foam to be used as a loading plate over the deck of the bridge while sliding one end of the eye bolt up through the foam and placing a small rod through the top to hold it on the deck of the bridge, while there is a hooked end to the eye bolt on the underside of the bridge where the bucket will be placed upon testing, with sand being used as the weight, which will be recorded in grams. During testing, it was discovered that the first cup that was attached to the eye bolt was too small and overflowed with sand, so a larger cup was needed to replace it mid-test. Results. This is a short clip of the moment the model bridge fails. Prior to this last 102 grams of sand being added, there was 646 grams, or 0.00633351 kilonewtons of force applied to the bridge, meaning after adding the final amount of 102 grams of sand and including the self-weight of the bridge failed under 0.010209 kilonewtons of force. Using the failure load of the spaghetti bridge and dividing it by its dead weight, the load to weight ratio can be calculated at 12.20 or 12/1/5. The point of failure happened in 2 places on the bridge: the deck on the right side of the bridge and one of the supporting trusses on the right side of the bridge, shown below. Here is a close-up shot of the failed sections of the bridge. After finding the failure load, free body diagrams were used to display the known reactions and forces applied to a particular node. Displayed here is one example of the free body diagram and its calculations. This slide displays the materials used in the SkySieve program when modelling the bridge, as well as the details and units used in the measurements. Here we can see the point loads that have been applied to the bridge by the SkySieve program. The image on the left depicts the displacement of the bridge members under maximum load, and the image on the right depicts the moments in the bridge under maximum load prior to bridge failure. The image on the left displays the axial stress that is placed on the bridge under testing, and the photo on the right displays the actual forces acting upon the bridge, with tension being displayed in blue and compression displaying in red, indicated by using the SkySieve program. During the testing of the bridge, a section on the right side of the bridge began to pull away from the bottom chord of the bridge truss, putting stress on top of the right supporting truss of the bridge and ultimately leading to the bridge's failure. This failure could be put down to two things. The first could be the bridge was not properly glued and fixed together, leading to the bridge deck pulling away from the trusses. Or the second reason could be that due to the angles in the trusses not being perpendicular and symmetrical, the forces were unbalanced on the bridge and stopped the bridge from being able to distribute weight evenly, leaving the right side of the bridge to support the majority of the weight. Recommendations that would improve the bridge's performance include ensuring angles of the bridge truss are perpendicular and symmetrical. This would add more strength as the weight would be able to be dispersed evenly. Ensure that the joints of the bridge are properly glued and sufficient amount of glue has been used. Gluing multiple strands of spaghetti for all the members of the bridge, not just the truss fan. This would strengthen the members of the bridge by a substantial amount and therefore allow a greater load to be added to the bridge. First contact was made with Sonia on the 12th of October through our student email, where we both gave a rough timeline of our plans in regards to the construction, testing and calculation of the bridge. The second time was on the 2nd of November, again through our student email, when we had both constructed and tested our model bridges. Sonia emailed me through a video of her bridge test. We discussed the bridge weight, failure loads, and the calculation of the load to weight ratio. To conclude, while the bridge didn't hold as much weight as hoped, the design skills, processes, and calculations that were learned over the course of the assessment will prove invaluable in the future. The manufacturing process of the bridge was quite tedious, but upon reflection, there are changes available that can make this easier in the future. This assessment highlighted the key structural and engineering concepts involved when constructing a model bridge and the key forces that apply. Thank you for listening.